Hey everyone, and welcome to section 1.6 of chapter 1, which deals with a library of parent functions. Okay, so the objectives of this section are to identify linear and squaring functions, be able to graph cubic, square root, and reciprocal function, and also to identify and graph step and other piecewise defined functions. And then lastly, to recognize graphs of parent functions. Okay, so let's begin. So linear and squaring functions. Okay, so one of the goals of this course is to help you understand and recognize the basic shapes of graphs of different types of functions. So, for example, you already know that the graph of the function f of x is equal to ax plus b is a line with slope m is equal to a and y-intercept at the point 0, comma b. Right? So we know that the graph has the following characteristics. We know the domain of the function is the set of all real numbers. And when m does not equal 0, so when the slope is non-zero, the range is the set of all real numbers also. We also can figure that the graph, if we set y equal to 0 and solve for x, the graph, we wouldn't realize the graph has an x-intercept of negative b over m, comma 0, and a y-intercept of 0, comma b, that comes from the function itself. And we know that the graph is increasing when slope is positive, it's decreasing when slope is negative, and it's constant when slope is equal to 0. So let's do an example. Write the linear function for f, for which f of 1 is equal to 3 and f of 4 is equal to 0. So we know that because the way that this is worded, we know that the function evaluated at x is equal to 3. So another way to write this is to say, okay, this represents a point 1, comma 3, and this here represents a point 4, comma 0. Okay? So we can just let x1, y1 be 1, 3, and x2, y2 be 4, 0, and then subtract the y's over the x's to find the slope. So we get 0 minus 3 over 4 minus 1, which is negative 3 over 3, which is just negative 1. That's the slope. Then we use point slope formula, where we put negative 1 for the slope, and we pick a point, 1, comma 3, and we plug in that for y1, x1, and distribute the negative, and then we get f of x is equal to negative x plus 4. Okay, so we can rewrite this in function notation. Okay, so when you graph it, it'll look like this, right? The y-intercept is here at 4. You get a slope of negative 1, which is down 1 over 1, down 1 over 1 point, down 1 over 1, and down 1 over 1. Okay, there are two special types of linear functions worth mentioning, which are the constant function and the identity function. The constant function has the form f of x is equal to some constant, so basically just a number. So when you get y equals a number, has a domain of all real numbers, and the range is just that number c. It could be, in this case, it looks like it's kind of like 1.3 or something. The graph of the constant function is a horizontal line, just like this. And depending on what c is, it could be here, up here, up here, or down here, who knows. Okay? And the identity function is basically like, if you think of someone's identity, or in math, it means when to say something is an identity, it has to do with like either it just equals itself, or sometimes the number 1 could be considered multiplicative identity. That's a different way to think about it. We haven't talked about that yet. So let's see. So in this case, identity function, you could see it as it's basically when each x coordinate equals the y coordinate. Okay. So the identity function. I mean, it sounds kind of fancy, but all it really is, it's a regular line with slope 1 and the y-intercept at 0, 0. So really it's just the graph of y equal x. Nothing crazy. So y is equal to x, right? Or f of x is equal to x. Meaning that every coordinate for x is equal to the same coordinate for y. So negative 1 is on it, negative 2, 0, 0, 1, 1, 2, 2, and so on. Okay, next, the graph of the squaring function, which is f of x is equal to x squared. It's a parabola, looks like a U, okay? And the domain of the function is the set of all real numbers. It's defined over all x. The range is, for just this specific one, is the set of non-negative real numbers. So the range is all values. F of x can take the values greater than or equal to 0. What else do we know? We know the function is even because it's a 2. It's a squaring function. And it has an intercept at the origin. So it looks like this guy. So here, some more stuff about this. Going from left to right. So from negative infinity to 0, the graph is decreasing. And from 0 to infinity, the graph is increasing, going up. Okay, there's a symmetry with respect to the y-axis. I'm sorry. That's why we know it's even. It has a relative minimum here at 0, 0, and this is the graph. Okay, so now we're going to cover cubic, square root, and reciprocal functions. How exciting. Are you excited? I'm super excited. Okay, so the following, we're going to summarize the basic characteristics of these three functions. So let's start with the cubic function. It's f of x is equal to x cubed, okay? And here are the characteristics. The domain is all reals. The range is also all reals. The function is odd, so it has symmetry about the origin. And the graph intercepts 0, 0, okay? So here we go. So it looks like this. It goes from negative infinity to positive infinity, increasing the whole way. It's symmetric with respect to the origin, and it has an intercept here at 0. So x-intercept is 0, y-intercept is 0. Okay. Next one is the square root function. What are the characteristics of the square root function? Well, the domain is a set of all non-negative real numbers. So what that means is that x can be greater than or equal to 0, because when you say non-negative, you're including 0. The range is also all non-negative real numbers. The graph has an intercept at 0, 0, and the graph is increasing from 0 to infinity. And what does this graph look like, you're asking? Let me show you. Okay, great. So it starts at 0, so when I take the square root of 0, I get 0. When I take the square root of 4, I get 2. Yeah? And continuing. So if I had 9, it would be 3. So it's increasing like this. Okay? And the domain is everything from 0 to infinity, and the range is from 0 to infinity. Okay, next is the reciprocal function. So f of x is equal to 1 over x, and it has these following characteristics. So the domain goes from negative infinity to 0, not including 0. Then it starts again at 0, but not including 0, to infinity. The range of the function is the same as the domain. So that gives you something to think about. That means that at 0, there is no graph. Okay? The function is odd, and it does not have any intercepts. See here, it doesn't have any intercepts. And the graph is decreasing from negative infinity to 0 and from 0 to infinity. And it's symmetric with respect to the origin. So you might think like, whoa, what does this look like? Well, let me do. Okay, so here it is, 1 over x, right? So if you get a negative 5, it's negative 1/5. So it gets close to the x-axis but never touches. So going from left to right, it decreases this way, and then it has this asymptote. We call this an asymptote. But basically, it does not ever hit the y-axis, but then it comes from here, and it goes down, 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 and approaches the x-axis but never touches. Okay, step and piecewise defined functions. Okay, so functions whose graph resemble stair steps are also known as step functions. And the most famous of the step functions is the greatest integer function, which is denoted by these like weird double bracket things here, and it's defined as f of x is equal to the greatest integer of x, where it's the greatest integer less than or equal to x. Okay, so let's say, for example, what does that mean? So if for x equals negative 1, the greatest integer that is less than or equal to negative 1, it's just negative 1. Remember the integers, they're the whole positives and negatives, right, including 0. So like negative, countably many, right? So negative like 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, and so on, extending out towards, you know, to the left and then the right, if you think about it on the number line. Okay, so what would be the greatest integer less than or equal to a negative half? So if you think about a number line and you were to plot negative 1/2 on a number line, the greatest integer that's next to this is negative 1. Okay? Then let's consider a positive 1/10. The greatest integer that's less than or equal to 1/10 would be 0, right? Because it goes 0 and then 1/10 and then 1 would be here, I guess. So let's think of another one. So 1.5, what would be the greatest integer less than or equal to 1.5? Well, in this case, it would be 1. So let's look at the graph. The graph is super interesting. So it looks like this, right? What? Crazy. Just looks like a bunch of like little steps, right? Where you include the left endpoint and you open circle the right endpoint. And this is because it's up here, okay? We keep seeing it. So the graph of the greatest integer function looks like this. And the domain of the function is all x. And the range is the set of all integers. See, the y's are only equal to integers, okay? So it has a y-intercept at 0, 0, and it has all this are x-intercepts, right? So the interval from 0 to 1, not including 1, is considered, you know, there are x-intercepts all in this interval. So the graph is constant between each pair of consecutive integer values of x. What does that mean in English? Okay, look, so from negative 2 to 1, negative 1, the graph stays the same. So here, the graph is always going to be, okay, here, f of x is equal to negative 1, negative 1, negative 1. Okay, here, the graph from 0 to 1, the graph is 0, 0, 0, 0, 0, 0, 0, right? Okay, and the graph jumps vertically 1 unit at each integer value of x. All right, so let's evaluate a step function. So let's say here, so evaluate the function when x is equal to negative 1, 2, and 3/2. So if I plug in negative 1, remember the greatest integer of negative 1 is negative 1. So you just get f of negative 1 is equal to negative 1 plus 1, so that's 0. That's because you're basically taking the greatest integer function and you're adding 1 to it. Let's do another one. So for x equals 2, the greatest integer less than or equal to 2 is 2. So then f of 2 would equal the greatest integer of 2 plus 1. So then that's 2 plus 1, and that's 3. So for x is equal to 3/2, the greatest integer that is less than or equal to 3/2 is 1. Okay? So 1 plus 1, and then you would just get 2. And you can verify your answers by looking at this graph. So we had, let's see here, negative 1. So x is equal to negative 1 right here. Okay, so the value of this was 0, and it is. And then for x equals 2, the greatest integer less than or equal to 2 is 2. Okay, so then we have here 2 plus 1. So actually at 2, it's not this, but it's actually up here. Okay, so the value of 2 is 3 because this is an open circle. Okay, and then finally the value at 3/2. So 3/2 is like 1.5 right here. So what's the value of the function at 3/2? And then you'll see it's over here too. Okay, cool. And then finally, parent functions. So all these, this is basically just summarizing all the graphs that we've covered today. We've covered 8 graphs. We've covered the constant function. We've covered the identity function. Oh, the only one we didn't cover was the absolute value, which is like a V shape. Okay, we covered the square root function. We covered the quadratic function, aka parabola, aka x squared. We talked about the cubic function. Okay, it looks like this. The reciprocal function, 1 over x. And then we definitely talked about the greatest integer function. Okay, so it's really important that you start familiarizing yourself with these graphs, because later on we're going to talk about transformations. I mean, I think very soon. I don't know if it's the next section or not, but we're going to start using these functions in a cool way. All right, so that is it for me. Good luck and happy studying, and I will see you on the next video.